So we've got a test on Thursday. Before then, a few things we've got due tonight. That is 6.1, 6.2 homework that's due tonight. That was related to the asymptotes and general setup, some facts about rational functions. Also due tonight, 6.4, which we're going to deal with 6.4 today in class. It's just some sort of different ways to think about rational functions, how the numerators and denominators are related. Since it's just ratios of polynomials, we know what happens with polynomials, thinking about the pattern of behavior, not just by the formulas, but we're actually going to take a look at the, just looking at the graphs of the components of a rational function and seeing if we can imagine what happens when we put them together. And you can compute them and obviously write out the formulas, but we're going to take a look at some of these just visually and see if we can determine the patterns from that, which is kind of cool. But also then the homework for that's due tomorrow night, and we've got an exam in class on Thursday. It is set up the same as the first exam, 21 multiple choice questions. I'll have Scantrons, make sure you bring a pencil. It covers material from 3 modules, although you notice we didn't spend very much time on module 6. It's about 40% module 5, or 4, well, 4 and 5. 40% 4, 40% 5, 20% 6, which that's, module 4 was the exponential and logarithmic functions, and all the writing models for that. We spent a lot of time on writing exponential models to fit situations, and then using logarithms. We didn't write logarithmic formulas from data, but using logarithms in order to solve exponential relationships. That's the most common use of them. So there's that. Module 5 was about a lot of time on quadratics, but some quadratic parabolas, along with other polynomial functions, and just things about end behavior and roots and where it's positive, negative, increasing, decreasing, those sorts of things. Not a lot of, it's not about how do you graph this, because I know, in terms of a multiple choice test, graphing things, you can graph on a graphing calculator, great. What I want to know is, can you analyze what you see? So you're going to be presented some graphs and answer questions about those. You'll be presented some formulas and asked about the behavior of the graphs, which you're welcome to use a graphing calculator on the test. So it's not about doing a lot of computations and figuring out a lot of coordinate pairs, other than do you understand what's meant by intercepts or roots or things like that. So to make sure that you can answer those questions, you're welcome to use a calculator. I don't think it's probably not necessary. It's not computational in nature, other than maybe a couple of questions where it's a lot easier if you had a calculator. But just in terms of logarithms, no, I'm not going to ask you to compute like log base 7 of 19 and get a decimal answer for it. You may need to write an expression like that, or choose the correct expression that would solve an exponential equation, but just written in some logarithmic form or another. And then module 6, about these rational functions, which again, I mentioned earlier, just ratios of polynomial functions, including constants, first degree, but also, quadratic, cubic, whatever, whole number powers of x, including 0 power constants, like 3 over x plus 7, things like that. Those are all rational functions. So module 6, just a little bit about those ratios of values and the tendencies in these, whether it's the limit notation or the slightly less formal as x approaches, kind of half sentence form, half math form, about tendencies in functions as x approaches either positive, negative, infinity, or specific numbers, where in rational functions, the specific x values we're often interested in terms of those limit statements are ones where the denominator is getting close to 0. Because denominators equal to 0 don't give us a value. But if you're close to 0, in these rational functions, you're going to have a pattern of numbers that either approaches positive infinity or negative infinity. So they grow or shrink, however you want to say that, grow positively or grow negatively without bound as you approach these denominators that equal 0 in most cases. And all the ones that we've dealt with So in any case, that's what's up for this week. Next week, we'll be starting in on Module 7, which is about trigonometry. So we'll be talking about angles and all sorts of different things, how to measure angles and side lengths and things like this. But that's coming up next. I did want to point out just one thing while it's up here. You'll see this at the bottom. Thursday, what is this, April 14th, it says Gateway. Originally, at the beginning of the semester, we were planning on having kind of a two-piece, called it Gateway exam. It just counts as homework. But what it is some of the nuts and bolts of the messy algebra that underlies a lot of what we're doing. So some of it includes like solving equations with square roots involved, or some of it is rationalizing denominators, things that you've probably done before that we haven't really needed to use in terms of what we've done in here, but they're just don't forget how this works sorts of things. And some of them maybe you need some more practice at. It's like a homework assignment, and it counts as a homework assignment. It's like 50 questions, I believe. You can work on the questions as many times as you want for full credit. It's not like a test, and it's not even like most of our homework is. It's more for practice, refreshing, whatever it might be on the assortment of topics. So there's 50 questions, but there's 4 questions that are on the same general topic at a time. So it's not really 50 different topics by any means. It's considerable in length because of those 50 questions, many of them have multiple things to answer, but it's not like it takes 2 days if you start it now. You could do it if you understand the topics in a couple hours, but that I just wanted to point that out. You can work on it as many times as you want. So thinking about, because I'm not going to have a chance to say this to you all on Thursday because your mind's going to be elsewhere at the beginning and you're going to be gone at the end. When we're done with our exam, if you want to, you can look ahead at Chapter 7 or Module 7, or if you want to take a look at that Gateway material. Let's see. Oh, there we go. It's, there's some exponents. So when you don't have any other assignments that are due right away, if you want to take a look and see how many of those you know, like you can see it's just, there's some distributing, multiplication of polynomial sorts of terms, factoring, simplifying, all sorts of just finding vertical intercepts of random things. Some of it is skills that we've used in the class and problems that we've done, kind of glossed over. Some of them are kind of trickier versions, just to make sure you're on your toes with the algebra that's behind a lot of what we've been doing. In any case, keep that in mind as something if you want to take a look at it. That's not due for a month. Let's see, 3 weeks from Thursday. And it is just a homework assignment. It's not worth like a test grade or anything like that. But it is extensive, and I hope it's something that you actually know how to do most of the topics in there. But if you don't, come to the Pathways Tutoring Center, or any tutoring center can help you with the skills that are on that. It's just general algebra and simplification sorts of skills. So that said, let's get back to Module 6, talking about rational functions. So I want to take a look at numerators and denominators of rational functions. And this looks like a mess on here. It's really hard to see. So because in order to see the details, it has to be large. And if it's large, then you can't see the rest of the sheet. So also on this, the idea is we're going to take a look at this function f of x. And the first questions here are asking questions about f of x itself. Given this graph, what are the roots? Where is it increasing, decreasing? What's the y-intercept, etc.? And that's just looking at this graph. But afterward, we're going to consider a graph, a function g, and g is 1 over f of x, and we want to answer some of the same questions about that, which is maybe kind of hard to do, especially if I scroll up and you can't see this anymore. So I printed out a copy of this, which is, this investigation is just 2 pages of paper. It's a little bit easier to see on paper, and also in terms of answering where is this 1 over f of x doing all these different things, where does it have specific properties. Might be easier to try to sketch out a graph, like not trying to type it on a computer, but like literally drawing out and trying to imagine what happens. So I'm going to do some drawing on the board. All right, so the first question on here, given this graph of f, and it doesn't say what its function rule is, but this is actually a linear function, not just something that is kind of linear-ish. But so we have this linear function f. Terminology that's important for your test, roots of f. What's meant by a root of a function? What's another word that we could use when we have a graph for what's meant by a root? It's a zero. Okay, zero of what? Zero of which variable? Yeah, it's where the y value is 0. Yeah, so it's where the y value is 0, or on a graph, that's going to be a spot located on the horizontal axis, x-axis. This time it's x, sometimes it's t, whatever that horizontal axis is called. So we're looking for a root, a 0, an x-intercept, and by 0 we mean a 0 of the function. The output value is 0. So any of those things are synonymous. And what is the value, in this case, of the root? There's only one. 4, right. So if we're talking about as an x-intercept, sometimes we might say 4, 0, like the coordinate pair. But if we're talking about just the root or a solution to an equation, like f of x equals 0, also the same thing, would just be x equals 4. So lots of times we just call it by the interesting part of that number, the part that isn't 0. The other part is 4. So the root of this is at x equals 4. What about the y-intercept? That's question number 2, A2.
0, 2.
Yeah, 0, 2. So sometimes if it says, what's the y-intercept? We can just answer 2 because it's understood. Yeah, it's the y part that's 2. That's the interesting part of that. So 0, 2 is the y-intercept as a point. On what interval of the domain is this function f of x increasing? Well, is it increasing? No. The whole thing is decreasing. From left to right, this is always going downhill. It's not a parabola that turns around and comes back up. So this one isn't increasing anywhere, which means it is decreasing. Well, it doesn't mean it's decreasing, but it certainly is decreasing everywhere. There aren't any places where it's constant, in other words. So increasing and decreasing don't cover quite everything. There's constant. It could be going straight across if it had like a zigzag pattern or something. But yeah, question A4, the interval on which f is decreasing. If we want to state that interval, it's intervals of the domain or the x value. So that's just x being anything between negative infinity and infinity. And so just interval notation wise, it's decreasing from negative infinity to infinity. Let's see, the other questions here. The intervals on which f of x is greater than 0. Any thoughts on this one?
Would it be above the x-intercept?
Yeah, all that stuff where it's above the x-intercept, so where we're above the x-axis. And so talking about it's going to be a part of the domain. The entire domain, it's decreasing. So this is not only where it's decreasing, this is the entire domain of function f. What part of that domain, from least to greatest, is f of x greater than 0? Yep, negative infinity through 4. So left to right is least to greatest for x. So I could say that f is decreasing on negative infinity to infinity. If I want to talk about where f is greater than 0, it's where the f of x or the y values are greater than 0. That's a part of that domain, negative infinity through 4. Now, I've talked with some people about this on homework questions. What sort of mark am I going to put here, a bracket or a parenthesis? Yeah, let's see. F of x is greater than 0. Is it greater than 0 at 4? No. So let me make two. There's one other statement I'm going to write up here that isn't on your sheet. But if it had said, where is f of x greater than or equal to 0? That's when I need a bracket, right? Infinity or negative infinity always get parentheses because you can never be equal to or at exactly infinity. It's not a spot, it's a concept that you can't reach. But 4, we can be at 4 or not. At x equals 4, f of x equals 0. It's not positive, it's not negative. So the difference between answering those two questions is the difference between the bracket and the parenthesis. At x equals 4, f of x is equal to 0. It's not greater than 0. So in this question, where is f of x greater than or equal to 0, I want to include the spot x equals 4 where it is equal to 0. Where it's greater than, we go up to but not including 4. I don't want to change this to a 3 and put a bracket because that would leave out all of the, all of this little stuff here. It goes all the way up to, 3.99999, however many nines you want to put, as long as it's a finite number of them. It's all still positive. But to express that in a nice succinct way, up to but not including 4 is this 4 with a parenthesis there. So if I wanted to say where is f of x less than 0, well, that's the rest of the domain, right? What we haven't talked about here, it's the stuff past 4, right? So if I want to know, fun stuff under there, where is f of x less than 0? From left to right, least to greatest, yeah, let's see, f of x is negative. Where's the leftmost place where f of x is negative, or where's the left boundary? 4. Yeah, 4 through infinity. So it's talking about this section of the graph. So left of this spot here, f of x is positive. Right of this spot, f of x is negative. At that spot, it's 0. But this is saying f of x is positive when I'm to the left of 4. F of x is negative when I'm to the right of 4. And this statement tells me that it's not like undefined at 4 or something. If I put this in there, I can say, oh yeah, so f of 4 is equal to 0. I know that from this statement here. Well, actually, I don't know that from that statement. I know that from the graph. But I can say that. That's why I'm including 4 here, because f of 4 is exactly equal to 0. All right, so this is a linear function, not too fancy. Now, if we're looking at instead a function where we're looking at the reciprocal of that, 1 over f of x. So you can kind of imagine, all right, 1 over these sorts of things. So I can even think, what we wrote here. If I'm between negative infinity and 4, I'd be doing 1 over some sort of positive number, right? If I'm picking x values past 4 and doing 1 over, I'm doing 1 over some negative number. So what happens when you do the reciprocal of a negative number? Is it positive or negative? 1 over a negative is negative, right? If I take a reciprocal of a positive number, I'm going to get positives. And what if I do the reciprocal of 0? Boom, black hole, universe explodes, right? So there's no value for 1 over f of x right at 4, but I know the sorts of values by sign that this reciprocal is going to have to the left of 4 and to the right of 4. So that at x equals 4, if we're looking at that reciprocal function, 1 over f of x, that's where we have those vertical asymptotes. That would be a spot where the function g of x, the reciprocal function, doesn't exist. So think about some of the questions that are listed here. I'm going to give you a chance to think about these on your own. You have a picture of f of x on your paper in front of you. So think about what happens to the value of g of x as, and remember this notation here, as we approach 4, as x approaches 4, and this little minus that's in the exponent position, superscript position, x approaches 4, but is slightly less than 4. So it's approaching 4 from the left, or is approaching 4 while staying less than 4, as opposed to the next statement, approaching 4 while being to the right of 4, or approaching 4 from numbers that are slightly larger than 4. Think about those values of the reciprocal function here. Those y values are outputs of this. And then what happens also as we approach either positive or negative infinity in that reciprocal function. So think about those, see if you can sketch a graph, whether by working out specific values or just kind of types of values and relatively how large they are compared to one another. But take a couple minutes. I'm going to put this projector here just to show that original f of x again. But our task right now is answer those questions.
Says the value of g of x approaches x
Mm-hmm.
is x to negative 4. Does that mean that it's a range of things, or is it still one answer? Like, what do you mean by an approach?
You can answer this either way. This is kind of a vague statement. So what is the, you can think of as what is the pattern of values, or what sorts of values does g of x have as I get closer and closer to x equals 4, but I'm on the left side of x equals 4? So you can say, well, it's like maybe around 5, then 6, then 7, or you can say it's, if you can say it's like, oh, it's getting really close to 0, or you could say it's getting really close to infinity. You could say it either as a set of numbers, or you could say it as a kind of an end result, like what it seems to be headed toward, like a goal value. But just as a note, that approaching, if you say something's approaching 5, that doesn't necessarily imply that it ever gets to 5. It's just saying it's approaching if you say something like that. It may or may not get there. That's a separate question. So you don't have to worry about how to compute what it gets to. It's more like looking for a trend. Alright, so again, we're looking at a picture here of f and being asked questions about its reciprocal. So just thinking about numbers and their reciprocals, if you take a reciprocal of a big number, it becomes a small number, as in far from 0 becomes close to 0, whether it's positive or negative. Far from 0, positive or negative, if you take a reciprocal, all of a sudden that bigness is a denominator, and you're close to 0. But your sign doesn't change. The other way around is it does a reverse. So if I started out with a small number, like let's say 0.5, 1/2, and I take its reciprocal, I've got 2. I'm farther from 0. What's the only 2 numbers I can take reciprocals of that its reciprocal is the same as itself? There are 2 numbers that have that property. 1 and -1, right. Reciprocal of 1 is 1, 1 over 1, 1 over 1. -1, same thing. 1 over -1 is the same as -1. So those 2 are their own reciprocals, and they're the boundary lines between, does taking a reciprocal make this bigger or smaller? As in, and I should say like in absolute value, or does taking the reciprocal make this number closer to or farther from 0? So looking at this graph here, and this kind of boundary line of here's 1, anything that's above this line, if I take reciprocals of these sorts of y values, they're all going to become closer to 0. But they're going to have to be positive, so they're all going to somehow squish in between 0 and 1. Here's -1 down here. I don't have a lot of y values that are farther away than -1 that are shown in this graph. But if I take the reciprocal of any of these that are more negative than -1, when I take the reciprocal, they're going to be still negative, but between 0 and -1. Like -2 becomes -1/2 when I take its reciprocal. Now, on the other hand, these things that are between 1 and -1, they're going to get farther from 0. So all of these sorts of values in here, between 0 and 1 y values positively, when I take the reciprocal of something like 1/2, it's going to become 2. Or maybe this is about at 1/4, its reciprocal would be 4. Or maybe I'm at an 1/8, and its reciprocal would be 8, way off the top of this graph. So you can maybe see four is kind of a key number here. 1 and -1, if I wanted to draw a sketch of this, oops, that's a positive one. I said -1 and wrote it. But I know this spot, 2, 1. If I take the reciprocal of 1, it's 1. So I'm still going to have a coordinate point at 2, 1 when I take a reciprocal, if I were looking for specific points. Or this one here at 6, -1. When I take the reciprocal, -1 stays -1. Oops, that's not down far enough. -1 stays -1. But every other point on this is going to move around. The points to the left of this that used to be up here in function f of x all get squished between 0 and 1. They have to fit in there someplace. The ones that were more negative than -1, when I take the reciprocal, are going to be stuck between 0 and -1. And they're stuck there. They're not going to suddenly become positive or ever turn into 0, although if you imagine this line goes down, 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 down. Out here someplace, there's a place where the y value is -1 billion. When I take the reciprocal of it, 1 over -1 billion. Well, if you tried to graph that, unless you zoom in really, really close, it's going to look just like 0. 1 over -1 billion, 0.0000001 with a negative sign in front of it. Pretty darn close to 0. So end behavior-wise, this is getting really close to 0. Even already here when I'm just at like 7, 8, 9, stuff like that. This side has to do the same. When I am back that direction, the y values or positive, and they're becoming more and more positive the farther left I go in the original function. They're becoming large positive numbers. When I take the reciprocal of large positive numbers, I get extremely small positive numbers, very close to 0. If I can imagine what's happening at x equals 4, nothing. That's the universe explodes and turns inside out sort of spot. But for all of these y values in this graph that are between positive and negative 1, excluding 0, when I take reciprocals of them, they become larger than what they were. They become, if they're between 0 and positive 1, they become positive values that are larger than 1. How big? I don't know. Between 0 and negative 1, they become more negative. How negative? I don't know, but negative. So if you can imagine what this graph looks like, this is sorts of graphs. Let's move this up a little bit. There's not a value for this reciprocal function when x is 4. Hand-drawn graphs, like we were talking about last Thursday, usually have a dotted line drawn in just to indicate, that there's this kind of do not touch zone. There's not a value there. So no matter what this graph looks like, it doesn't actually have a value anywhere on that vertical line. Now, I can pick any value up to but not including 4. 4.00000001 has a value that's ever so slightly negative in the original. So that means it's going to be a huge negative number, as in far from 0 negative number. Here, someplace down there. And vice versa, if I pick something that's ever so slightly positive. So you can kind of reconstruct this graphically by having a couple key points, because ones are their own reciprocals. But just answering these questions, what does the value of g of x approach as x approaches 4 with a negative? That's usually read as x approaches 4 from the left. As x approaches 4 from the left, or as x has values increasingly close to 4 but is to the left of 4, we're getting larger and larger. So I can say that f of x is increasing, right, as we approach 4 from the left. If I were just looking at this graph and not this sketch that I've done already, if I was just looking at this, I'm like, well, as x approaches 4 from the left, I'm getting values like 0.01, 0.001, 0.0001. So what happens to my reciprocal values? 1 over f of x. That'd be like 10, 100, 1,000. And they can be as large as I want. The closer I get to x equals 4, the closer these values get to 0. As long as I don't touch 4, I don't run into a 0, which is good in terms of conceptualizing this reciprocal. But to answer that first question then, what happens when x approaches 4 from the left? Well, normally what we say, and I'll write the short notation for saving space, as x approaches 4 from the left, in this g of x function, my y values are headed up toward positive infinity. I'll put a positive sign there for emphasis, but you don't have to write a positive sign. On the other hand, the next question, what if I approach 4, but from the right, approaching 4 while staying larger than 4? Now it's an x value of 4, so in this graph here, I can say, oh, that's going down. If I were looking at the original graph and trying to make that determination, say, well, what if I'm approaching x equals 4 from the right, or looking at values near 4 but to the right of 4? I've got things like y values of, in the original graph, maybe like negative 0.5, and then negative 0.1, and negative 0.01, and negative 0.0001. Those reciprocals are negative 2, negative 10, negative 100, negative 1,000, etc. All the way down there. So as we approach 4, but use values that are only larger than 4 in that approach, we say that g of x heads toward negative infinity. So this is the kind of abbreviated, very mathy notation as opposed to the, you can write it as a sentence notation, but those mean the same thing. So these two questions here, I could answer this one with positive infinity and this one with negative infinity. These are rewriting the whole things in like all math as opposed to half English, half math. They're saying the same thing. But we can either see that looking at the original graph and imagining reciprocals, since that's what this function g of x is. You could write out a table of values if you wanted to for points around 4, like we could have worked out specific values. I was kind of saying them aloud. What if x is, what if this y value is something specific? But you could pick like, write a formula for f of x, and then come up with a y value for a bunch of values near 4, and then see if there's a pattern. But if you're going to do that, just in terms of, what do you mean find a pattern in them? Well, if I'm approaching 4, but staying to the left of 4, maybe I'd be looking at values like, what if x is 3.5, or 3.9, or 3.99, or 3.999. This is x approaching 4 from the left. If I go down this table, I'm getting closer and closer to 4. I'm not actually running into 4, because if I were to use 4, this would be mystery bad number doesn't exist. But the rest of these, I don't have a formula written out for f of x, so I don't know what numbers precisely run into these, but these are getting, the reciprocals are getting larger and larger and larger. They're headed towards positive infinity, because I've got all positive values. This is more positive, this is more positive, etc. If you had a formula for f of x, you could do this numerically also. You could see the trend in the numbers. But those are getting larger and larger and larger, which is talking about this. But you can kind of see what has to happen in this graph because of how reciprocals work. If I take a reciprocal of something between 0 and 1, it's going to be larger than 1. If I take a reciprocal of something larger than 1, it's going to be between 0 and 1. So there's no escape for these points to go anywhere else other than just between 0 and 1, because all of those y values in the rest of this linear function would be greater than 1. And as they keep getting greater and greater and greater, the reciprocal keeps getting closer and closer and closer to 0. So these other two questions here, 3 and 4, there's a fifth one, which is sketch, which we already did. But what is the value of g of x approach as x approaches positive infinity, or as x increases without bound? So thinking about as x increases without bound, I know my original function f is becoming more and more and more negative, farther from 0 negative. So if I want to answer what happens to the reciprocal of that, I have 1 over extremely large numbers, which visually that's what's going on here. I've got negative numbers, but hardly so. They're getting closer and closer to 0, but staying to the left. If you wanted to, in fact, as x approaches positive infinity, this g of x is getting closer and closer to 0. If you wanted to make a statement in sentence form, a lot of times what might even be done is say, well, it's getting closer and closer to 0, but it's staying less than 0. Right? If you wanted to say something about that, you could say that. Now, it is approaching 0, but you could also say it's approaching 0 from the left, or meaning from something less than 0. I say left, so I'm thinking just like, what is it approaching, and having a number line in my head. Now, it's approaching 0 from below. Below is less than 0 in y value sense. Similarly, that question 4, Roman numeral 4 here, what's the value of g of x approaches? X approaches negative infinity, or as I go farther and farther to the left? In this graph of function f, I was getting larger and larger positive numbers. So the reciprocals of those were positive numbers also, but closer and closer to 0. And so talking about this end behavior here, is what it's asking about. What's happening when I go out this way? Well, it's going to stay positive, but hardly so. It's almost 0. I don't really have a good spot on the graph to write this, but let's write it up here. As x approaches negative infinity, function g of x has values that get closer and closer to 0. If you wanted to specify, though, they're getting closer and closer to 0, but they're always positive. They're always a little bit above 0. It's approaching 0 from the positive side, or from above, visually speaking. So you can say either just 0 or 0 plus. It sounds weird to have 0 with a positive or negative sign. It's not saying that 0 is a positive or negative number. It's just talking about how we're approaching this value of 0. This little exponent position of a plus or minus is indicating a direction of approach as opposed to the sign of the number itself. All right, so I don't want to do that part D. We don't need to do that. But take a look at the backside here. Question 4 that has a graph of a parabola and then 5 over said parabola's function. You don't have to write the formula for it, but just do some of the same imaginings that we did with the linear question. See if you can figure out what would go on with this one. Maybe start by thinking, when would this reciprocal not be defined, if anywhere? And then what sort of values would be their own reciprocal? And where would the function be otherwise? And once you've got that, go ahead to number 5, which has a function f and a function g that are both linear, and wants you to make a fraction out of them. So that one's tricky. Also notice, just in case you were looking up here or on your paper, it's also quite small. This is 5 over f of x as opposed to 1 over f of x, so it's 5 times the reciprocal. But the same general shape is going to happen regardless of whether that's a 1 or a 5. Just kind of like x squared and 5x squared are very similar. All right, so I've got this graph of a parabola, which, just thinking parabola notation, this is decreasing and then increasing from left to right. It's always concave up. It's got a vertex at x equals -3, it looks like. And that is -3 comma 0. So it doesn't have any roots other than just its own vertex. But most of this graph is then pretty far from 0. There's only this little tiny section here in the middle around the vertex where I've got values between 0 and 1. It doesn't have any negative values. So thinking about reciprocal sorts of things, 5 over these things, it's going to be, well, it's not going to be negative anywhere if I do the reciprocal of this. Because I've got all positive and 0 value to start with. But I do have that one 0 value, right? At x equals -3. So I know there's not a value to 5 over f of x or anything over f of x at x equals 3. And everywhere else it's going to be positive because I'm taking reciprocals of positive numbers and then multiplying by 5, if you want to think of it that way. What I'm saying is like 5 times 1 over f of x is the same as 5 over f of x. So that's what I was saying. Oh, reciprocal and then multiply by 5, that would be the same because of how we multiply fractions. So just thinking of the sizes of numbers, if I were going to try to sketch a graph here, it'd only be between, this isn't exactly at x equals or 0 comma 1, but it's pretty close to that. So just kind of between 0 and -6 is where it looks like this graph is between 0 and 1. Meaning this point's going to kind of, if I didn't have this 5 here, that point would kind of stay put, and I'd have another point over here that kind of stay put. And everything between is suddenly going to be large and positive, and everything outside is going to be small and positive. Only, well, I'm going to redeclare that to be 5. Everything in between here is going to be large and positive. Everything outside is going to be smaller and positive. And it has to stay positive. So there's not too many ways this graph could look. Or in terms of end behavior, didn't draw very carefully, there we go. Both the left and the right ends as I look either toward positive or negative infinity for x, since this original graph is positive all the time, and the ends are extremely large positive numbers, then when I do its reciprocal, even when I multiply it by 5, those ends are going to be extremely close to 0 numbers. I'm going to say above 0 if you want to write, that like approaching 0 from above, from positive numbers. We can write that. Most of the time you won't see that written in these limit statements, but it's kind of helpful. It's not wrong. It's just people tend to not give as many details. But then there's this domain issue. The domain of this reciprocal function is only from -infinity to 3 with a parenthesis, or -3 rather, and then from the other side of -3, parenthesis -3, up through infinity. The function value doesn't exist at 3 because I'd be doing a reciprocal of 0. -3, sorry. Let me write that down so I keep saying +3 there. But the closer x value gets to be -3 in the original graph, the closer everything gets to be 0, but it's positive. So I've got extremely small positive numbers. So when I do the reciprocal of them, I get extremely large positive numbers. And so I could say, if I'm approaching -3, whether it's from the right or approaching -3 from the left, either one of those, I'm headed towards positive infinity, or my values are increasing without bound. Oops, I didn't write the g of x in there. So these statements say that around -3, from either side, my y values are going up to positive infinity. This statement is saying is that whether I look to the right or the left, the y values are getting close to the x-axis, flattening out. So these are just fancy ways to say what you can see visually in the graph. Now, if I were to write out an expression for f of x would be something like, some number or another times x plus 3 squared, right? Vertex of the original was at x equals -3. I don't know what the leading coefficient is. I don't really know any other specific points on here. There's not any nice grid points that are easy to pick from, but some positive number, maybe it's 1/2 x plus 3 squared, or 2/3 x plus 3 squared, or something. Some sort of positive number times x plus 3 squared. If I wanted to write out g of x as a formula, then I could say, oh, it's 5 over f of x, so 5 over something times x plus 3 squared. So looking at something like this, if I had a formula written out, regardless of what positive number a is, I know it's a positive number, I know that when x gets extremely large, this is a fraction that's bottom heavy. It's a huge number on the bottom, and it's still only 5 on the top. Even if I simplify with that, it's just a constant of some sort. So this means that, subbing in numbers, you can see, oh, yeah, as x gets larger and larger, or as x gets more and more negative, either one, this denominator is going to be a huge positive number, meaning the fraction is positive, but extremely close to 0. We could have done the same with the previous function also. In fact, this one is probably say, oh, this is a slope of -1/2, right? Goes from 2 down to 4, 0, 2 down to 4, 0. And you can even just use the grid lines to count. That's a slope of -1/2. Y equals -1/2 x plus 2. If you were to write in that formula for g of x up here, it would look kind of weird. -1/2 x plus 2 to have a fraction and a fraction. But regardless, even in that not so nice answer key form, that wouldn't be something you'd see in the back of the book. I can see that if I plug in x's for that, as x gets larger and larger, the denominator of this gets more and more negative. As x becomes more and more negative, the denominator gets to be a huge positive number, which reciprocals of those then, 1 over those, or those as the denominator, means that those far from 0 results have extremely close to 0 values. Now, on the other hand, take a look at question 5. Given these graphs of f and g, f is the one on the left, g is the one on the right, we want to determine what h of x equals f over g, f of x over g of x, what that graph would look like. Now, that's maybe a mess, but maybe you can also see, oh, well, f of x and g of x are both just linear functions. If I wanted to write a formula out, I could probably write their function rules. F of x, just looking at it, seems to go diagonally through 1 squared at a time, which are worth 1 in both directions, so this is a slope of 1. Y equals x plus 5. And looks the same here, y equals x plus 2. Okay, so I could write out a formula for this ratio then. H of x would be x plus 5 over x plus 2. Or maybe it'd be easier to see if they're all in the same graph, and you see this in the 6.4 homework. You'll see two functions, two linear functions on the same graph, and ask these sorts of questions. But f of x at any x value is just exactly 3 larger than g of x is. X plus 5 versus x plus 2. All the y values, they're parallel lines. So it's always 3 larger. But when you've got 3 larger and you're talking about 2 versus 5, f of x over g of x is 5 over 2. Numerator is 3 larger than the denominator. That's 2.5. If I were to go out farther to the right, at some place it's going to be 13 and 10. That's 1.3. At another point, it's going to be 103 and 100. I'm picking numbers that I can divide easily, which is 1.03. The farther you go to the right here, that 3-unit difference as a ratio between two large numbers is not very much. Like, if one person's a millionaire and the other is a millionaire plus $3, it's essentially the same, right? So that ratio is approximately 1. That seems sensible. Well, one's 3 larger than the other, so why isn't it 3? It's not how much larger subtraction, it's how much larger as a multiple. So thinking about exponential sorts of things. And that's why the graphs of these kind of look like exponential graphs. They're these curved shapes. So what we're looking at is the proportion. Now in these, the proportion, it's not by finding a multiple. It's like, oh, one is 3 larger than the other. But it's that same idea. When I'm looking at how much larger is one than the other and dividing to find it, I find that ratio. And one number 3 larger than the other. Whether I'm looking at extremely large numbers or extremely small numbers doesn't really make too much difference. When they're both negative and they're 3 different, I'm going to get a ratio that's about -1. Or positive 1, and they're both negative. When they're both positive, like they are when I go off to the right, and I do a ratio and the numbers are 3 different from one another, like 103 versus 100, 1,003 versus 1,000. Or going back the other direction, -1,003 versus -1,000. And it'd be the other way around, but they're both going to be approximately the same when I divide them. It's going to come out close to 1 when the numbers are themselves quite far from 0. It's only this center section when I can get things like 2.5 or, well, when would this ratio f of x over g of x be undefined? For what value of x would f of x over g of x be undefined? When can't I do that division? At what x value? Yeah, -2. You can see in the graph here, when x is -2, g of x is 0. So I don't want to do that. So in terms of piecing together what this function looks like, I maybe know that like at the ends of the graph, ratio-wise, the values when I divide them, it's going to be pretty close to 1. So I'm going to put in a 1 here. And this is not a do not cross. This is a helping me draw this sort of line. If this is 1, I know that the ends of the graph are pretty close to 1. Because relatively speaking, when I've got extremely large positive numbers for 2 things that are kind of the same, you can, let's see, what do we write? Say this h of x was x plus 5 over x plus 2. Numerator's 3 bigger than the denominator. When x is extremely large, the fact that I'm adding 5 versus 2, in other words, doesn't really make a whole lot of difference. They're about the same. When x is -2, I'll just say -2 is here. That ratio doesn't make any sense. So again, helping me draw this, I'm dividing this graph up. Now if I'm looking at, maybe a couple key points, like the vertical intercept of these two, 5 versus 2, when x is 0, 5 and 2. Those are the only things that make this function work when x is 0. I've got 2.5. 0, 2.5. Or I could plug in some other values. But for instance, if x is 1, I get 6 over 3. All right, 6 over 3 is 2. If x was 2, I get 7 over 4. It's like 1.5-ish. Whatever, but I'm going to get smaller and smaller positive numbers, not increasing all the way to 0, but getting closer and closer to 1 as I go to the right. On the other hand, if I were to go a little bit negative, between 0 and -2, like if x is -1, this would be 4/1. If x were a little bit more negative than that yet, like if x is -1.5, let's see, what is this? 3.5 over a half, so that's 7. It's going to continue to get larger. As I get closer and closer to an x value of -2, but stay to the right of 2, both of these things are going to be positive. But it's going to get larger and larger when this denominator is near 0. Now, the other half of this graph is something we hadn't had in the other things we looked at. Notice that this numerator could equal 0, and that's okay. Denominators of fractions aren't supposed to be 0. Numerators of fractions can be 0, and it would be if x was -5. This would be -5 over, or if I had h of -5, would be 0 over -3. What's the value of 0 over -3 said more normally? Yeah, that's just 0, right? That's not undefined. 0 divided by -3 is 0. 0 on top of a fraction is 0. So all this means is if I'm back here at -5, this function has a y value of 0. And that's okay. You can't really see that from this graph, but it relates to the fact that this point exists, and this is the numerator of the function, so I'm getting 0 over -3, which is 0. Now, if I were to go farther to the left than that, I'd have two negative numbers. Like, let's say at -10, this looks like -5 or so, and -8, if that makes sense. If I had -5 and -8 in a fraction, in that order, -5 over -8 is positive 5/8. That's like up here someplace. As I go farther to the left, x's are both very negative numbers, like -100 plus 5 over -100 plus 2. Those are both -90 something. So when I divide them, I've got approximately +1 when I go out really far to the left. It's going to be slightly less than 1 because when x is a negative number, this numerator is like, when x is negative, this is two negative numbers and this one's more negative than that one. So I've got something that's slightly below +1. On the other hand, if I get close to -2, but stay to the left of -2, if I'm to the left of -2, but not very much, like at -4, that denominator is going to be negative, but the numerator is going to be positive. So I have +1 over -2, for instance, -0.5. Or if I get closer yet, like h of -3, I'd have 2 over -1, which is -2. And the closer I get to x equals -2, but stay to the left of it, the more negative my results are going to get, because this denominator is getting extremely close to 0, and it's negative, while the numerator is small, but not nearly as small, and it's definitely positive. So the graph of this altogether would look something like this. We can see when this would be positive and when this would be negative by looking at the values of x's, and when it would be undefined or when it would be 0, looking at the numerator and denominator. But you can also just take specific kind of numbers, like, well, maybe -5 is important for something. Maybe -2 as an x value is important for something. But what if I look around those? Or like we did with the others, and say, well, what about like, where are these numbers that are their own reciprocals? Well, I'm not taking a reciprocal of any one thing, I'm taking a ratio of two pieces. So if we're looking for where do these have the same value, they don't anywhere. These don't have the same value anywhere. As x gets extremely far from 0 in either direction, as a ratio, the values are pretty close to one another. So that's where we get pretty close to 1. But there's no spot on these graphs where they have the exact same value. The numerator is always 3 larger than the denominator. So we don't have any spot that just turned into itself on the graph the same way we did in the others. All right, so in any case, you can do this analysis purely from the equation, from writing out the formula or the function rule. But you can maybe do some just kind of figurings by looking at this, even if you don't want to write out a formula or you're not quite sure how to, like with the parabola ones, I don't really know what that first value is because I can't see the coordinate points, they're not nice round numbers. You can kind of get an idea of how large or how small those reciprocals are, or how large or how small the ratios are by estimating some points and seeing what the pattern and the values are. You can definitely tell where they're going to be undefined, where there would be something in the denominator equal to 0, at x equals -2, for instance, in this one, and a trend toward the ends, and when we get near to that undefined value. Those are things to look at for these sorts of functions. All right, so that's all I wanted to say about those. But you've got a test on Thursday. Like I said, it's set up the same as your first test was. 21 questions will be out of 100 points, but they're 5 points each, so it's kind of, you can get 105 on the test. Bring a pencil because it's Scantron. There's no like trick questions. If you skip over one word, it all means the entire opposite of what you read, other than if you miss a negative sign, I suppose, but that's not a trick, it's just read the numbers that are there. This review packet's been posted for a while. I put up the key to it just a little bit ago. I did want to point out there are a few questions on here that are not included on your test. It's just, and one you might have looked at and said, what on earth is that? I'll scroll to it quickly because it's a picture. Because I don't like these questions. If I can find it, these with these bottles and stuff, there's not a question like that. So you can not worry about question number 26. I also think there's one at the end that was tacked on. Yeah, this question 40 is about difference quotients. We'll talk about difference quotients again. There's some in the gateway test. It's really a gateway test, sort of like just some algebra manipulations. There's not a question about those on your test either. So 26 and 40 on that. I'd say don't worry about, but number 39 probably looks familiar based on what we were just doing. Here's an f of x and a g of x. They are on the same graph, and they looked kind of like the ones that we were just dealing with. One's just 3 units higher than the other, same slope. Actually, it's 2 units on this one. But just taking a look at these and answering some questions about them. Keep in mind, like I said, you can do them purely from the graphs. You can do them purely from the equations. Or you can kind of do a mix of the two and put together all the things that you know about functions when you're dealing with that. But don't forget about the stuff that we did earlier on, like how to write exponential functions from tables of values. The questions on the test are actually in like sequential order. It starts out with the module 4 stuff, then the module 5 stuff, then the module 6 stuff. This review kind of jumps all over the place, so I don't know, maybe that makes it more of a challenge. I don't know. I didn't put together the review and it's a PDF, so I couldn't change it easily. I just left it as is. But if you have any questions on this, Pathways Tutoring is open a lot. Let's see, we've got hours today from, well, it's open right now for another 20 minutes, 10 to 12:30, 2 to 5, lots of hours tomorrow, and, well, not any before our test on Thursday. But this is just on your iMath main page right under the calendar here. So, in any case, if you have any questions, you can also email me, post on the forums if you're working on the homework questions. It's easier to like link to the questions that way. And I will see you on Thursday for the test. Oh, regular class time, 7:30. Yep.
I haven't really been here the past week-ish. Sorry about that.
That's okay.
Putting my